Okay, so here we are in Unit 8. We've gone over what pH is and what it tells us about a solution. We have talked about strong acids and bases. We know the 7 strong acids, and we know that any soluble hydroxide salt is considered a strong base. And so today we jump into calculations using weak acids and bases. We're going to talk about mixtures of acids and bases and what's present and how we determine the pH of those. Um, so let's go ahead and jump in and talk about acids and bases and mixtures. So the first thing to remember about weak acids and bases is that what we're talking about here is equilibrium. Okay, we know that weak acids only partially dissociate. And so that means that we have an equilibrium where we have the undissociated acid along with hydronium ions and the anion or the conjugate base all present in our solution. We also know that weak bases react with water to increase hydroxide ion concentration. So this means that in a weak acid equilibrium or a weak base equilibrium, the concentration of the hydronium ion or the concentration of the hydroxide ion is determined by concentrations and the equilibrium constant, the Ka, if we're talking about an acid equilibrium, or the Kb if we're talking about the base equilibrium. So in terms of a weak acid, what does that look like? Well, before dissociation, we have just the weak acid. After dissociation or at equilibrium, we have both the weak acid, the hydronium ion, and the anion all present. This has a really small Ka, unlike the strong acids that we've talked about already, which means that this is reactant favored. There's going to be a lot more undissociated acid than dissociated acid. In fact, we generally define weak acids as dissociating less than 5% in solution. So, just as with any equilibrium reaction, we can write a K or an equilibrium constant expression. And in this case, it's going to be the hydrogen ion or the hydronium ion concentration times the anion or the conjugate base concentration divided by the weak acid concentration. As I've said before, College Board uses the hydronium ion convention. Hydrogen ion is also acceptable. So there are tables published for these dissociation constants. Just like all our other tables, they're at a given temperature. So when you look up a Ka for a weak acid, it's going to be at 25 degrees Celsius. One of the things that we talk about with weak acids is this idea of percent ionization. So percent ionization is just a measurement of how ionized that acid is. What extent does it ionize? And so in order to calculate percent ionization, we just determine the hydronium ion concentration, divide it by the acid concentration, and multiply by 100%. So the percent ionization is dependent on the strength of the acid and the initial concentration. If you have two acids of equal concentration, the weaker acid is going to have a lower percent ionization. But if you have two samples of the same acid, so we have two samples of acetic acid, for example, and they're at different concentrations, the lower concentration solution is actually going to be more ionized as a percentage. So the solution that has the lower concentration will actually have a higher percent ionization. So as we add water, we're pushing that equilibrium to the right, and that's going to cause a higher percent ionization. Okay, so those are some terms that we talk about. Now let's talk about, we'll come back to the idea of conjugate bases. And you'll hear me use that term throughout this unit. When we talk about the anion of a weak acid, we're always going to call it a conjugate base. The weaker the acid, the stronger its conjugate base. And we've taken that on faith so far this year. Now let's talk about why that actually is. So if we look at Ka and Kb, we know that the Ka and Kb of conjugate pairs. The Kb of the conjugate base times the Ka of the acid is equal to Kw. So this means that they are inversely proportional. So as Ka gets larger, so the acid gets stronger, Kb gets smaller. As Ka gets smaller, so the acid gets weaker, Kb of the conjugate base gets larger, so it becomes a stronger base. And if we really want to think about why that is, the definition of a strong base, or the definition of a base, is its ability to increase hydroxide ion concentration in water. So the conjugate base of a weak acid is very likely to be able to pull a hydrogen ion off of a water molecule to make hydroxide ions in solution. So if we know either Ka or Kb of the conjugate, then we can find the other. If we know one, we can calculate the other, and this is going to be a useful tool for you. This equation, Ka times Kb equals Kw, is one of the equations on your equations and constants sheet, so you can expect that you will need to apply this. Okay, so we've talked about weak acids. Let's talk about weak bases. Remember, weak bases, we're not so much talking about dissociation as a reaction with water that produces a hydroxide ion. So one of our classic examples of a weak base is the ammonia molecule. And the ammonia molecule, because it has that lone pair on the central nitrogen, is very adept at pulling a hydrogen ion off of a water molecule, thereby producing the ammonium conjugate acid and hydroxide ion. So just as we could write a Ka for any acid dissociation, we can write a Kb for any weak base reaction. So our Kb is always going to be the conjugate acid concentration times the hydroxide ion concentration divided by our weak base concentration. And Kb is what we call the base dissociation constant, or the base equilibrium constant. So far we have Ka and we have Kb. Now let's talk about how we can use all of this information to calculate the pH of either a weak acid or a weak base solution. So remember that this is an equilibrium problem. So our primary tool is going to be our ICE table, just as it was for any equilibrium problem in the last unit. So we're asked to find the pH of a half molar solution of acetic acid, and we're given the Ka. As with any equilibrium problem, our first step is going to be to write the dissociation equation, or write the equilibrium equation. So in this case, that's acetic acid dissociating into the acetate ion. There's your conjugate base, and the hydrogen ion, or the hydronium ion. There's your conjugate acid. Okay, so now we write our ICE table. We know that the initial concentration of the acetic acid is 0.50 molar. The initial concentration of both the acetate ion and the hydrogen ion are 0. We also know that the change is going to be a decrease of X for acetic acid and an increase of X for both acetate ion and hydrogen ion. And then we're going to write our equilibrium line. So we know that at equilibrium, our new concentration is going to be 0.5 minus X and X and X. Now, because this is 0.5 and the Ka is so very small, we're going to make the simplifying assumption. So we're here at equilibrium, we're going to plug all of this into our Ka expression. So our Ka expression says that Ka is equal to acetate ion concentration times hydrogen ion concentration divided by acetic acid concentration. But again, we're going to make that simplifying assumption that 0.5 minus X is approximately 0.5. And that allows us to solve relatively easily for X, which is also our hydrogen ion concentration. And we find that X is equal to 3 times 10 to the negative third molar. So we're going to go back and do our 5% check. And 3 times 10 to the negative third divided by 1.8 times 10 to the negative fifth times 100 is in fact less than 5%. So we made a good assumption. So we now know the hydrogen ion concentration is 3 times 10 to the negative third. But the question asked us to find the pH of the solution. So in order to find pH, we're going to take the negative log of the hydrogen ion concentration, and that's going to give us 2.52. So just like all of our equilibrium problems from the last unit, you're going to use that ICE table, initial, change, and equilibrium. With weak acids, we're going to use the simplifying assumption unless we find that it can't be used with that 5% check. Okay, because we can calculate Ka and concentration, if we have concentrations, we can also calculate Ka. So that means that we can actually calculate Ka from the pH of a solution. So we know the pH of this 10th molar solution of formic acid is 2.38. Now, this being 2.38, and this being 10th molar, we know that this must be a weak acid, because if it was a strong acid, it would have a pH of 1. Also, it's not one of the strong acids on our list. So we know that Ka is equal to the hydronium ion concentration times the formate ion concentration divided by the formic acid concentration. So in order to calculate our Ka, we need these 3 equilibrium concentrations. So the first thing we're going to do is recognize that we can find the hydronium ion concentration, which is the same as that formate ion concentration, from pH. Because pH is the negative log of hydronium ion concentration, which means hydronium ion concentration is equal to 10 to the negative pH. And so our hydronium ion concentration is equal to 4.2 times 10 to the negative third. Because this is a dissociation reaction, we know that the hydronium ion concentration and the formate ion concentration are the same. And we also know that the initial concentration of our formic acid was 0.10. So we know the formic acid concentration. We have just found the hydronium ion concentration and the formate ion concentration. We can plug all of that into our Ka expression, and we can solve and find that the Ka for formic acid is 1.8 times 10 to the negative fourth. So as with everything in chemistry, we need to be able to approach it from both directions. If we're given pH, can we find Ka? If we're given Ka, can we find pH? Okay, so we now know how to find the pH or the Ka of a weak acid. Let's talk about weak bases. The most common weak base that we'll work with in this class is ammonia, but there are lots of other weak bases out there. You'll notice that all of these weak bases have this lone pair. So that's one of the ways that we can easily identify our weak bases, is that they have a lone pair that is available to be an electron pair donor. So we have Kb. Finding Kb, using Kb, we can find hydroxide ion concentration and eventually POH and pH. So we'll go through a practice problem with this one as well. We're asked to find the pH of a 0.15 molar solution of ammonia. So first thing we're going to do is write our equilibrium expression. We have ammonia plus water yields ammonium ion and hydroxide ion. From that, we can write our Kb expression, the ammonium ion concentration times hydroxide ion concentration divided by ammonia concentration equals 1.8 times 10 to the negative fifth. As always, we're going to set up our ICE table. We have our initial concentrations of 0.15, 0, and 0. We know that the ammonia is going to go down by an amount, X, and the ammonium and the hydroxide ion are both going to go up by that same amount. At equilibrium then, our ammonia concentration is 0.15 minus X, but that's going to be approximately 0.15, again, a very small KB. And our ammonia and hydroxide ion concentrations are going to be X. Now we're going to plug all of that into our KB expression. 1.8 times 10 to the negative fifth equals X squared over 0.15. And we're able to solve for X, and we get 1.6 times 10 to the negative third. That 1.6 times 10 to the negative third is our hydroxide ion concentration. We can find POH by taking the negative log of that concentration. And then from POH, we're going to subtract from 14 to find that the pH of our solution is 11.2. So we can find pH of an acidic solution or a basic solution. Now we know how to find them, whether it is a strong acid or a strong base, or weak acid or weak base. Strong acid, strong base, we assume concentration of hydronium ion or hydroxide ion is the same as the concentration of the acid or base. For weak acids and weak bases, we need to set up our ice table and use our understanding of equilibrium. So what happens? Well, before we start mixing them, let's jump ahead and talk a little bit about the acid-base properties of salts. So we've emphasized all along through the year the idea of conjugate bases and conjugate acids. And this becomes important when we start talking about the acid-base properties of salts, because salts, ionic compounds, can behave like acids or bases. So let's first talk about the type of salt that is going to be a neutral salt. If our cation came from a strong base, so potassium, sodium, lithium, magnesium, calcium, any of those would be strong bases when we put them with hydroxide. And our anion comes from a strong acid, so that would be things like the chloride ion, the nitrate ion, the perchlorate ion, the chlorate ion. Both ions are going to be neutral, and therefore our solution of that salt is going to be neutral, because these salts just dissociate in water, and that's the end of the story. On the other hand, if we have a cation from a strong base, so again, sodium, potassium, lithium, magnesium, but the anion is from a weak acid, so something like acetate or cyanide or fluoride, that anion from the weak acid is going to behave like a base, and it's going to take a proton from water, and we're going to have the weak acid and the hydroxide ion. And so our cation in this case is neutral, but our anion, that conjugate base of a weak acid, is going to behave like a base, and so we're going to have a basic solution. If we have the conjugate acid of a weak base, so we have something like ammonium, and the anion is from a strong acid, so again, chloride, nitrate, sulfate, our cation is acidic and our anion is neutral. And so our solution is going to be acidic, because the acidic cation is going to act like a proton donor. Our ammonium, that weak acid, is going to donate a hydrogen ion, and we're going to have a conjugate base and a proton. Our last case is if we have conjugates of a weak base and a weak acid. So we have something like ammonium acetate or ammonium cyanide. Our cation's acidic, our anion is basic. So we have both an acidic contribution and a basic contribution. So what's our pH going to be? Well, if the Ka is bigger, the solution will be acidic. If the Kb is bigger, the solution will be basic. And if the Ka and Kb are equal, the solution is going to be neutral. As an example, the Kb for ammonium and the Ka for acetate are actually the same, and so that would be a neutral solution. Okay, now if we have a mixture of acids and bases, first thing we have to do to try and figure out pH is we have to figure out what species are present. So if we were to mix sodium hydroxide and hydrochloric acid, we have sodium ions, hydroxide ions, hydrogen ions, and chloride ions. And we need to determine what reactant is in excess. So if we would be given molarities and volumes. And then whatever is in excess, we're going to use the new concentration of that excess reagent to determine pH. If those reactants are equimolar, then we would use the concentrations of the conjugate acid or the conjugate base to determine the pH of our new solution. Okay, so we are going to pause here, and we will have this conversation about acids, bases, and calculating pH in class tomorrow.